momentum. The symbol is P. It is a vector, so I use an arrow to represent it, right? This is a vector, and it is a product of mass multiplied with the velocity. It is actually a vector quantity. And the SI unit for momentum is SI unit is actually kilogram meter per second. Okay. Momentum could be also stated in terms of kinetic energy. Okay, momentum is a product of mv. So we also know that kinetic energy is equal to half mv squared. So it's quite close to the term of mv. So we're trying to state the momentum in terms of kinetic energy. So what we did is maybe you try to express the kinetic energy in terms of mv. So if in terms of mv, you will get it v squared divided by m. I write it in this way. M squared v squared. So m and n can be could be cancelled off, and eventually you will get back half mv squared, right? So I purposely express it in terms of m squared v squared, so that m squared v squared is equal to p squared, because p is equal to mv. Right? P squared divided by 2m. So that is the how you relate the kinetic energy to momentum, or momentum to kinetic energy. Okay. Now let's move on to another term. It's called it as impulse. Impulse is actually change of momentum. So impulse, I can write it as I, change of momentum. So as I mentioned before, every time you see this change mean we are using final minus initial. So final momentum is mv, initial momentum is mu. So if v is the final velocity and u is the initial velocity, so this one will be the final momentum. This is the initial momentum. For example, you are playing badminton. For example, this is a shuttlecock of a badminton. It is moving in this direction with the initial speed of u. So I would like to change the momentum of this object. The object is shuttlecock. How you change it? You have to apply the force to it. So the force you apply is you use a racket to hit it, right? Apply the force to the object and hit it, so that the object would change the momentum or change the velocity to v. Okay, m cannot change, m is constant. In order for you to change the momentum of this shuttlecock, you have to apply the force to it, and therefore the force that you apply is used to change the momentum, right? But the rate that you change the momentum is called it as force, right? Or in the other word, the product of force and the time is actually equal to the change of momentum. The first expression is also referred to Newton's law. Okay, Newton's second law is said that the force is the rate of change of momentum. That net force that you apply is equal to the change of momentum, rate of change of momentum, which is mv minus u divided by t. So here mv minus mu is actually the change of momentum divided by t. So that's why you will get this. So if I multiply the term of t with f, you will get the change of momentum. So happen impulse is also defined as a change of momentum. Therefore, the impulse is also equal to the product of f multiplied with t. This is called it as impulse. All right, product of f multiplied with t is a change of momentum, and impulse is the change of momentum. Therefore, impulse is the product of force multiplied with t. The delta t is actually the time contact, right? For example, you use a racket to hit the shuttlecock. So what is the time contact during the collision, right? So that is a time contact, the force that you apply to contact with the shuttlecock. Unit of impulse is same as momentum. The impulse is defined as the change of momentum, right? So the unit for impulse is still same as the momentum. That is kg meter per second. So this force here, okay, it can be the average force, because sometimes the force you apply is not a constant force, or it could be a constant force. So it depends on the case. So this one F could be a constant force or average force that you apply to the object. Okay, principle of conservation of momentum. So according to this principle, in an isolated system, so what is isolated? No external forces. Okay, no external forces. So in order to apply the principle of conservation of momentum, the system must be an isolated system, right? Total momentum is always conserved, right? So in an isolated system, total momentum is conserved. Okay, conserved means constant, is always equal. right? So which means the momentum before the collision is equal to the momentum after the collision. Momentum before the collision is equal to the momentum after the collision. So if let's say I have two objects, maybe I have two cars, car 1 moving with the velocity of u1, and then the mass of car 1 is m1, and car 2 moving with the initial velocity of u2, car 2, right? And the initial velocity of u2 and the mass is m2. And if the velocity of u1 is greater than u2, so there's a possibility that u2 will collide with car 2. So they collide. So after the collision, so it could be either they stick together, move with one common velocity, or they're moving with two different velocity. Okay, let's say now they are moving with two different velocity, v1 and v2. Okay, so m is still the same. V will be the final velocity after the collision. So momentum is conserved. So before the collision, total momentum will be m1 u1 plus m2 u2. After collision, total momentum will be m1 v1 plus m2 v2. It's conserved means it's equal. This is what we call it as principle of conservation of momentum. If let's say the case of car 1 and car 2, after the collision, it is both cars moving, stick together and moving with only one common velocity, then the momentum, total momentum expression, it could be written as m1 u1 plus m2 u2 is equal to m1 plus m2 multiplied with v. Both of the object will move with only one velocity. So, okay, so this is the principle of conservation of momentum. So how do you know that when I should use this, whether it is they are moving after the collision, they are moving together or they are moving with different velocity? Then you have to refer to what type of collision is that, right? So basically, collision, there are two types of collision. The first one is called it as elastic collision. The other one is called it as inelastic collision. Okay, whenever you see that the collision, elastic collision, momentum is conserved, and kinetic energy is also conserved. And for elastic collision, object will move with different velocities after the collision. However, for inelastic collision, momentum is conserved. So no matter whether it is inelastic or elastic collision, momentum is always conserved. But for inelastic collision, kinetic energy is not conserved. To remember this, kinetic energy for inelastic collision is not conserved. Okay, not conserved. And for perfectly, so usually the case that we're referring will be referred to perfectly inelastic collision. So what happened to the object is the two objects will stick together and move with only one common velocity. Move with one common velocity. Let's look at this elastic collision. So if for elastic collision, actually momentum and kinetic energy is conserved, right? So if let's say I write down the expression, okay, by applying the principle of conservation of momentum and principle of conservation of kinetic energy for an elastic collision. So what is going on here? So for an elastic collision, so you can see that elastic collision, both momentum and kinetic energy are conserved. So if I apply the principle of conservation of momentum, P is momentum, yeah, momentum. If I apply the conservation of momentum, so before the collision, the total momentum is m1 u1 plus m2 u2. So after the collision, the objects will move with different velocity. Therefore, the momentum after the collision will be m1 v1 plus m2 v2. Okay, this is my the equation that I'm going to show you. Okay, then also for elastic collision, the kinetic energy is conserved. Therefore, half m1 u1 squared initial kinetic energy for the first object. For the second object, initial kinetic energy is half m2 u2 squared. So it's equal to half m1 v1 squared plus half m2 v2 squared. Now I'm trying to derive another expression which is in the linear form so that you can use it for this elastic collision. Let's look at the principle of conservation of momentum. m1 u1 plus m2 u2 equal to m1 v1 plus m2 V2. So I move the M1 to the left-hand side of the equation, M2 to right side of the equation, and therefore I will get M1 U1 minus V1, M2 V2 minus U2. Okay, I call this as first equation. Same as principle of conservation of kinetic energy. I move all the term of M1 to the left-hand side of the equation and M2 to the right-hand side of the equation. Right? Then you will have M1 U1 square minus V1 square equal to M2 V2 square minus U2 square. This is my second equation. Right? I'm trying to simplify it. So I use equation 2 divided by equation 1. So when I divide, M1 can be cancelled off. So I will have U1 square minus V1 square divided by U1 minus V1 equal to V2 square minus U2 square over V2 minus U2. So this is A square minus B square. So my A square minus B square. So A plus B, A minus B. So we use this to expand it. So same as here. So you have U1 plus V1, U1 minus V1 divided by U1 minus V1 equal to V2 plus U2, then V2 minus U2 divided by V2 minus U2. Right? You can see that, oh, I can actually cancel off. Then this one cancel off. Right? You reduce the equation to U1 plus V1 equal to V2 plus U2, right? Now I move all the U to the left-hand side, V to the right-hand side. So I will get U1 minus U2 equal to V2 minus V1, or you can write it as U1 minus U2 equal to negative V1 minus V2. Now you can just remember this relation. U1 minus U2 is equal to the negative of V1 minus V2, right? This one is only valid if the collision is elastic collision. Every time you see an elastic collision problem, so directly apply the principle of conservation of momentum and this relation to solve the problem.